now?
No.
Hello? Test?
Test.
Yay. Good. Is it? Oh, it's
5.
Oh, your phone says 6:31.
So is mine. Okay, never mind.
Oh,
Clock's wrong.
microphone is off. People starting to wander in.
Test. Okay. Hey, everyone. Hi, I'm Bhargav, conference staff. Anyway, so this is Jason Fennell. He works at Yelp. He's a search team lead at Yelp, search team manager. That's right. I keep saying the wrong title. Anyway, he likes long walks on the beach and discussing his feelings, but he won't be talking about any of that today.
Thank you, and thank you for the intro. Can you guys hear me over this? Yes, okay, I really can't tell. So yeah, I put that in a bio because I went to my alma mater and they asked me for a bio, and I was like, whatever. And thus far, every bio I've put it in, it's gotten quoted in the talk, so, or printed out in a lot of pamphlets. Anyway, so I'm going to talk to you about search at Yelp and do a little basic introduction to information retrieval, and then talk about basically information retrieval as applied to particular problem domain, namely local business search. Again, as Bhargav said, I'm the manager of the search and data mining team at Yelp. I've been there about 3 years and worked on pretty much anything and everything related to search on the site in that time. And I graduated from Harvey Mudd College in 2008. So quick, super fast intro on what is Yelp. It's a site that connects people with great local businesses. You, the consumer, want a veterinarian. You go on Yelp, search for veterinarians. Now your parakeet won't die. The veterinarian wants more business. They can come and advertise on our site. Same model as Google, sponsored, slot above search results. Yelp is growing like crazy, which is really good for me. So we had more than 63 million monthly visitors last month, more than 21 million reviews. And I joined somewhere right there. So it's been a hell of a ride thus far, and it just keeps getting faster. One point I also like to make is that Yelp is not nearly all restaurant reviews, and that's what people tend to. That's a major use case. But like, I moved to the Bay Area, got this job, found my doctor through Yelp, find bars through Yelp, you can find most local things. No, this talk is not a local business, so that won't quite work. Is this working? Yeah. Okay. Cannot tell. All right, so that was Yelp. Now what I want to talk to you about is actually search at Yelp. So, and I have to apologize in advance. The examples in this talk are going to largely be Harvey Mudd and Claremont Central, because that's where I went to college. That's where I know a whole hell of a lot of things. And I was slightly too lazy to rework every example in the talk. So it is not meant to be a slight to this great institution, just merely my laziness. So Patty's Mexican Foods is a great burrito place near Harvey Mudd College. A lot of people spend a lot of time there and a lot of money there. So when you search for burrito in Claremont, California, it's really good that Patty's comes up first. And basically we're going to be exploring why does this happen, why wouldn't this happen, and stuff like that in this talk. So basically the actual technical interaction that's happening here is you're sending burrito to your browser, and your browser sends HTTP GET to our front end Apaches, and then they start filling in a bunch of data from DB, our spell suggest service, our talk service, and then Lucy, which is our main business search. Lucy means business. Also a slightly less joking title or reason for the name is that Lucy is based on the open source Lucene project, which provides sort of the basic nuts and bolts for a search engine, and we've built a lot on top of that. And I'm basically going to be talking about how Lucy works all day and try to distinguish her with this little Lucy comic book character icon that I attempted to draw in Google Present. So you'll have to deal with my bad art the whole talk. But to start with, I'm going to be talking about information retrieval in general and kind of what it takes to build an information retrieval system or a search engine. And I particularly like this picture because you're kind of searching for a needle in a haystack or diamonds in a pile of shit with this, and it's a good representation of what we do. So the pieces that make up an information retrieval system are sort of an indexing side and a querying side. Indexing, you suck in a bunch of data, you put it into a format that will allow you to retrieve it efficiently, and then you query on that, find all your relevant documents, and score them. And that's what we're going to run through first. So again, another Harvey Mudd College Central example. So we have this. Let's say this is our corpus. We have 3 documents in our corpus: Harvey Mudd College, Scripps, and Pitzer, and they have corresponding document IDs and some text associated with them. So, and then the sort of information retrieval task is we want to find all the documents that contain Harvey Mudd, or we want to find all the documents that contain Best and Campus. And I should say right now, I will use the term document and business interchangeably throughout this talk. A document is a unit of retrieval in an information retrieval system. A business is the unit of retrieval for Lucy. And I spend so much time working with Lucy that the two things are synonymous in my mind, and I can't tell when I'm saying one or the other. So just fair warning. So how would we do this? How would you go about identifying, like, what are all the businesses that have Best Campus, or what are all the businesses that have Harvey Mudd in them? Documents. So one great way is grep. For like a corpus this size, well, you can get grep up and running in about 2 seconds, and it's really, really fast. And grep is great, but as your corpus starts to grow and grow and grow, grep runs into this problem that it has to look over literally your entire corpus in order to find your results every time. So we want to do better than that. And intuitively, the problem is we're looking at all this dross that we don't care about when we only care about these particular terms. So how can we pull out the documents that they contain those terms in a quick way? I like the Flash. We can build an index. So this is just an index of that corpus I showed you before. So we can see if you search for Harvey Mudd, or let's see, Best Campus, you see Best has documents 0 and 2. Campus has documents 1 and 2. Now, when you want to actually query on this, what you do is you just look up all the terms in your query, and then you do a linear time merge, like in merge sort, and then you're left with 2, which is Pitzer College, which is the only document that matched. You can do the same thing for Harvey Mudd College. And this is sort of the core of the indexing side. This is what backs most search engines out there. And you can get really crazy, make this really fancy sort of, these are called posting lists, or the list of documents that have a particular term in it. You can do all sorts of compression on them. You can do prefix compression on these, because this gets to be gigabytes and gigabytes, and you want it to be small enough to hold in memory, or at least parts of it in memory. And this is called an inverted index. Now, why is it called an inverted index? It's because information retrieval people really like their jobs and want to make things seem really intimidating and scary. It's actually just an index. It really is. You're inverting the original corpus, but it's still an index like you find in the back of a book. Let's see. All right, so that's enough to get you relevant documents. So we can find like all the businesses that have or all the colleges that contain the words best campus, or all the businesses that mention burrito. But that just gets us a set of documents, which is sort of the Boolean retrieval model. Here's everything that is relevant to you, and we'll just hand you back a huge bag. Now what we want to do is we want to score that set of relevant documents. We want to know which one is the best one. And intuitively, so the way to do that, if you want to find what's the best Mexican place, what's the place that's most relevant to the term burrito, well, you could start by saying maybe just the thing that mentions the word burrito the most times. So if you say burrito a lot, then maybe you're relevant to the term burrito. And that's actually like a reasonable place to start. So you can say the TF, or term frequency, of burrito in the business patties is just the number of times the term burrito occurs in the business patties. And that works fine, and you'll find places related to burritos. Unfortunately, if you search for good burrito, or even worse, the burrito, suddenly everything goes to shit. Because now you're searching for burrito, and it's fine, but you're also searching for the. The appears a ton of times in every document in your corpus, and now you've essentially just randomized your order, and everything's bad. So this is where we introduce the concept of DF, which is essentially a way of figuring out the importance of different terms in your query. So DF stands for document frequency. It's a corpus-wide measure. You say the document frequency of burrito is just the number of documents that the term burrito occurs in. And this can be defined in a number of different ways, but we'll just use that one here. So now what you want is you want to say if a term occurs lots of times in a document, then that's good. We're gonna boost that document up in our results. So burrito occurring lots of times, that's good. And if that term appears a lot across the corpus, then that's bad, because that term means nothing. It means nothing to see another instance of that term. So we're going to say divide out by the document frequency. And that's where TF-IDF comes from, term frequency inverse document frequency. And that's kind of the start of the scoring for most search engines out there. So to make that a little more concrete, let's work an example. Juanita's 3 is another burrito place near Harvey Mudd College, and HMC is Harvey Mudd College. And so we see that good appears 10 times for Patty's, 5 for Juanita's, 20 for Harvey Mudd College, and then 100,000 times in the corpus overall. And burrito occurs 10, 5, 1, and then 20 overall. And basically what happens is when you divide out by how often it occurs in the corpus, you end up with a 0.5 score for Patty's, 0.25 for Juanita's, and 0.05 for Harvey Mudd College. Basically, the term just drops out and stops affecting your scoring, which is exactly what we want. However, this is an extraordinarily contrived example. There's no reason that just because Patty's is the best burrito place out there, that it'll have the burrito occur the most times in its review text. So we need to start, yeah.
So in the previous slide, is the document the businesses that they learn the way how the scoring is done, they can.
So again, when I say, yeah, document is, so again, like the unit of retrieval and the information associated with a particular entity. So in our case, a business object is like all the review text, all the like category information, the name, and basically everything we know about a business. And we're just matching over that text. The business owner should not be able to manipulate review text on the site. We have a whole other team that deals with making sure of that.
Is there a description field that they can go on and
There's an about this business section that they have. They can add information to, and actually is searched over. We downweight that content very, very highly because of worrying about spam and stuff like that. So yeah, in theory, they could do like keyword SEO on us, but if we started finding that, then they'd have other problems. Did that answer your question? Cool. So, and yeah, beyond just TF-IDF of like basic word relevancy, there's a lot of other things we want to take a look at. Like maybe something says burritos lots of times, but it's a one-star business. So we don't. That's not what we want to show you. Number one. So we can use those little star ratings that you give us along with reviews, and say the average review of the average rating of a business should be one of the signals we're looking at, or maybe a slightly more complicated function of it than average review. We're a local search engine, so location matters a little bit. If you're searching for pizza in Champaign and we return you results in Chicago, that's not a very good thing. Also, if you're searching in a particular neighborhood and we return you results out of that neighborhood or far away from that neighborhood, that's not a good thing. Slightly less obvious is category. So Yelp maintains a category ontology. So we, of like Mexican restaurants or Mexican places are restaurants, et cetera, and every business is categorized in a few of these categories. So we know that Patty's is a Mexican restaurant. Also, we can figure out, based on user behavior, what sort of the categories associated with certain queries are, and understand that if you're searching for burrito, you're probably looking for Mexican places, and we can boost up Mexican places in the results. So these are a bunch of sort of extensions to the basic like academic IR models that, I mean, I can convince you that they're reasonable, but how do we know if the actual implementations are helping? We need to be able to measure this somehow. And a good place to start is precision and recall. So precision is basically the accuracy of what you've returned. How many of the results that we gave you are actually relevant to your search? Recall is a little bit different. Recall is, out of all the relevant documents in the corpus, how many of them did we return to you? And then let's work another example. So if these 9 documents are our whole corpus and you searched for restaurant, we sent you back a sushi place, Thai place, Italian, plumber, hotel, and Vietnamese. The precision is 4 out of 6 because the plumber and the hotel were not relevant. So there's only 4 out of 6 relevant results. The recall is 4 out of 5 because we returned 4 relevant documents, but there's a 5th relevant one, this Japanese place, that we didn't return. Precision and recall are really useful concepts, but in practice, they're very hard to calculate. So for instance, we would have to, for every query, find every relevant document to that query in our corpus. That's not something we can do even with an army of human raters. So in practice, we don't calculate these, but we do talk about them when discussing projects because there's a trade-off here. You can very easily get perfect recall by always returning every document to the user. But that's not very useful. That's very bad precision. Similarly, you can kind of get very good precision by only ever returning one document, but that's not really what people want. So what do we do in practice? Well, a few different things. First of all, we track a lot of aggregate metrics about click-through rates, dwell times, bounce rates, and things like that. We can cut up in a whole bunch of different ways. So we can say, like, in this area, are people, when they're searching for these types of categories, spending longer or shorter amounts of time on biz pages? And from that, figure out, oh, we kind of suck here. We need to fix this thing. Another big area is A/B testing that I'm going to talk about a little more on the next slide. And then I like to mention this, that because I don't think it's mentioned a lot when people talk about IR or search, is that intuition is a really large part of it. Intuition and understanding your problem domain and understanding what the issues you're facing are. Because like if you read a lot of blog posts about this stuff, it sounds like everything is totally scientific and followed logically. And I think there's definitely a place for intuition and inspiration in this. But I skipped a little over A/B testing. The idea of A/B testing is that we have a new feature. Say we're going to rank things differently. And we want to know how it actually affects some key metrics, say click-through rate. So we'll launch this to 5% of users. So 5% of users will always see this new feature. And the other 95% of users will just see the old stuff. And then we can track aggregate metrics in the two different cohorts and say, oh, the click-through rate is statistically significantly higher with the new feature. Let's launch it for everybody. So you can see here a screenshot of the experiments framework we have built with most of the compromising information removed. So there's two different cohorts here. We see their click-through rate over time, and the bands around them are the confidence intervals. So you see the sort of orange one really is a lot better than the black one, so we'll probably be going with whatever that feature is. In practice, it is not nearly this clear-cut. They're usually pretty close to each other, but we like to see this sort of thing. And also notice the Yoda quotes. Key part of the feature. So that's actually enough for you to go and build your own search engine. You kind of know how to build an inverted index. You know how to query on it, and you have a basic idea of how to score things. And I mean, to do that, like to build the inverted index I showed you there, that's like 20 lines of Python code, maybe. Querying isn't much more. And I actually encourage you to go build this stuff. Well, obviously I think it's really fun, but I think other people will think it's fun. And as you start sticking in real world data and trying to run different queries on it, you start to see problems crop up and gain a better understanding of how these systems work. So now what we're going to talk about is what happens when you stick a whole lot of real world data in here. So Yelp, again, has more than 21 million reviews. We have hundreds of queries coming in every second. What happens to an information retrieval system when you do that? Well, things go wrong. And things go wrong in subtle, like they go wrong obviously, but there's inside that wrong, there's like subtle, even worse wrongs that you don't realize at first. So you see a pile of elephant shit, but there's a guy under that. So, more metaphors for what it's like to work on search. So I like this example as an example of where TF-IDF kind of falls over. So the burrito was awesome, but they really need a plumber after I use the bathroom. So what does this do? The burrito query is still fine, but now what happens when somebody, and this is a review of a burrito place, what happens when someone searches for plumber? Well, this is going to match when we just do the basic querying on our inverted index and the posting list. This is going to come up because it contains the word plumber now, and we've kind of introduced some of these other signals. So maybe this is a really highly reviewed burrito place, and it'll pop up to the top of results for the plumber query, and we look really stupid, and I feel bad. So I think this is just one example of where you start with this basic, conceptually clean, kind of academic model that works pretty well in most cases, and you kind of have state space, and TF-IDF just plain covers this, and we've added some scoring stuff that gets you a little farther, and we're just trying to carve away with more general solutions to kind of close in this space of things we do bad on. I like to think of it like inclusion-exclusion, if you guys remember that from discrete. So for this sort of thing, actually, again, mentioned we understand the categories associated with most queries. So we understand that the plumber query is associated with the plumber category. So when Mexican places come up, we can fold them out of results. And that helps with this problem a lot, but doesn't quite eliminate it. So now I'm going to kind of run through a bunch of different examples of the Yelp-specific search problems and that we see, and some solutions we've come up with for them, and also just some problems that are still real problems for us. So first of all, name matches. A huge portion of the searches on Yelp are for exact names of businesses. You're not searching for burrito or Mexican. You're searching for Patty's, or you're searching for Harvey Mudd College. So we want to really give a big advantage to name searches. We don't want, just because there's like other matching terms, things that match on review text, to win over Patty's or Harvey Mudd College. So for instance, Harvey Mudd College matches for Harvey Mudd College. And we can do this by creating another separate index. We talked about having just an index for all your text. You can create another parallel index. So this one the first one just contains review text, and the second one contains titles and business names, and you query on that one first and give matches there a higher weight and push them up in results. And so that works pretty well. But you start getting into cases like this. This was actually a good search. So you search for butter, and this bar, butter in San Francisco, comes up. Very stiff drinks there. But it's right on the edge, right? So what if you searched for restaurant and there was a place that called themselves restaurant? And if you don't believe people do that, I tell you they do, and they piss me off. Or salons that call themselves salon. Or what? Exactly. So you need to make sure that you want to bias towards the name matches, but you don't want to let people SEO the names of their businesses. So we have a concept of a common term. So a restaurant is a common term, so name matches shouldn't be boosted as much. You're just browsing for restaurants. And we can sort of look at click-through behavior and try and automatically detect what's a common term and what is not. This is another fun one. So the standard is a hotel in New York, and you can see that it matches for a query in New York City. But if you search for the standard hotel, suddenly it disappears. And it's actually like down here at result number 4, which may be below the fold of the page and is just bad. So what's going on here? Well, we do a conjunctive query up here. So you search for the and standard and hotel. Now sort of the alternate default is a disjunctive query, the or standard or hotel, which suddenly we're like shooting down the precision recall trade-off way towards recall because, well, let's say we stop where out the, but then we still match on everything that says hotel, and that's no good. And so we're doing this conjunctive query here, and we try and match on the name first, but hotel doesn't incur in the name of the standard. So it doesn't match when we're like boosting names first, and then it just has to fight everybody else when the standard is searched for across review text and names and everything else. And there's other places, other hotels that contain the word standard somewhere in their text and match on this and are just better quality hotels than the standard. So one possible solution here is to detect category words in the query and automatically pull them out and say, we'll match on this name and boost on this category or something like that. This is currently a problem on the site right now. It's something we're working on, but if you're interested, it's still a problem. So we're doing text retrieval. So actually processing your text right is something you have to keep in mind and be very careful with. I don't know if you noticed way back on my inverted index example, but there was a word, I think, house. It was house period, because I didn't do any sort of punctuation removal. Well, that's a problem, because if the user searches for house, they're then not going to be matching any documents that had house at the end of the sentence. Similarly, if you don't case normalize, and you're just like hacking together your own search engine, that you're going to not be seeing results coming back that you should be. But beyond like basic punctuation and case normalization, there's other stuff like stemming. So you really want plumber to match plumbing. They're both, you and I both understand that they're both sort of instances of this concept of plumb, this Platonic concept of the plumber. So you need to make sure to have a good stemmer. This becomes more and more of a problem as Yelp expands to more and more languages. I think we're in 7 now and expanding rapidly. So there's good stemmers in English, but this problem is currently giving me nightmares. Beyond stemming, there's you need to do, you want to do a little more advanced than just dropping of punctuation. So in and out should match in and out with dashes, without dashes, and all jammed together. You'd think that, small details like this you can almost brush under the rug, but in practice, they come up a fair amount of times, make you look stupid, and you'd be surprised at how much time in the real world you spend like optimizing these little things. I've spent 3 weeks getting this similar thing working for apostrophes, and well, now it generalizes across all like apostrophes and hyphens and stuff like that, but you'd be surprised. And now we can get to like even more crazy and interesting things, like when people just don't follow directions, which happens a lot. So they search for a burrito near Claremont, California, in San Francisco. And we actually catch this case because they use the word near. We're like, okay, you said near, we'll move that all over into the right box and search in the place you actually meant. I think this is also a great example of sort of, as someone who works on a real-world search engine, basically your job is to make a machine that, given a small hint, reads the person's mind. I'm sure that Hofstadter would be getting mad at me for using that terminology, but that's sort of how I think about it. You're trying to figure out what the user meant, not what they said. And so we're actually working on this one too, to automatically detect like when there's a location type thing in the left box and just move it over. But you have to be careful. Make sure that you don't just always recognize location and move it over, because it would kind of suck if you could only search for New York pizza in New York. And speaking of location, we're a location-aware search engine. We only do this local search. So how can you make that work with this retrieval model that I've talked about? So let's say you want to search in a lat-long box. That's kind of a nice abstraction for I'm searching in this particular area. This is supposed to be a minus sign. Sorry. And I'm going to get latitude and longitude backwards. Don't hold it against me. So say we're there and we want to search in this lat-long box around the point. Well, what you can do is discretize latitude and longitude to 2 digits past the decimal or something like that. When you say, I want to search in this box, you can build a query that says, match on 34.10 or 34.11 or 34.09 all the way down, and match on all the longitudes. And then suddenly you built a query that will find things in this box. Meanwhile, you also have 2 more parallel indices that store latitudes and longitudes and all the documents associated with them. And really easily, you can build for yourself a search engine that's location aware. Maybe not the most optimal way of doing this, but very easy to build. But just because you can search in a box doesn't mean you're done. You have to figure out what box you want to search in. So I live in the Mission in San Francisco. This is a search at my apartment. And the Mission has a lot of good burritos. They're basically everywhere. And I know that I should not have to walk more than 2 blocks to get a burrito, and certainly not more than 4 blocks to get a fantastic burrito. So when I search for a burrito right around my apartment, I get a pretty tight map that just shows a few blocks around me, and that's good. But if I search for dog parks around my apartment, Mission isn't really a neighborhood where people want to go walk their dog. It's a little sketchier than that. But that doesn't mean we just want to give up and be like, oh, this address is very, very specific, so we're not going to search around very much for you. You can do that yourself. Well, the user's first reaction is going to be zoom out, zoom out, zoom out, and find better results. So let's just do that for them. So we search out and say, all right, you're going to have to walk a little ways, but this is where you can find dog parks around there. And we call this bounce out. Works for name matches, for instance. So Claremont is over here, and you don't want to be searching out this far for the default Claremont area, but if you search for Disneyland, we should be able to find it for you. Gets a little more interesting when you're not just doing name matches, but we can do this sort of on categories as well. So if you search for snow tubing in LA, default LA search area is kind of like about where my hand is, and it's snowed in LA like once in the last 10 years. You're not going to find places to go like tubing in LA. And what we can do is we can say, oh, we can look at the category distribution of results and say, oh, we don't see anything that looks like what we think should be associated with snow tubing. Let's keep looking farther and farther out until we do. I don't really want to give more details than I actually gave. I'm like already a little bit like, I don't know if I should say that much. So think about it. See if you can do it yourself. See if you can do it yourself. But I showed you lots of yeah.
How do you know when to stop? Like many of them, all them. Then when you said dog parks, you had like.
Oh.
So how do you know where to stop? Like, do you have some numbers?
So why is this matching on 137 or whatever, like this one, or 10?
I'm talking about math.
Mm-hmm. 10 out of like this one that matched 40. So we're displaying 1 through 10 of 40. So the 40 is the number of everything, like everything that matched. We're only displaying the top 10 views, like on Google when there are like a billion things matched. Here's 10.
I'm talking about the map. So when you have the
If it's showing 10 versus 20, that's just me not picking the results per page to 10 on every one of my examples. It's sort of a user selection of how many results they want displayed on a particular page. It's like how do we know not to like keep making this bigger? We'll show 10. If 10 matched, if like the top 10 that matched will show, unless the user wants to see 20 or 30 or 40, in which case that's how many will show on the map.
then why less on dog parks?
Less on dog parks. Probably because they're hidden or like really far on the sides. So please don't hold user interface stuff against me. They don't let me get anywhere near design, and that's a good idea. So yeah, it can be pretty confusing when we have a little pie slice way off in the corner there, and we probably shouldn't be doing that. But it's kind of the trade-off between we want to only show you exactly the area we searched in, but it's hard to it's kind of weird to like spin around the pie slices or something like that. So I showed you a bunch of examples of where we did well on this bounce out thing, but of course, like everything else, it breaks. So this is a search for live music in Suffolk County, New York, which is here. And we're telling you that the best place for live music is a nice 3-hour swim across the Long Island Sound, which is not ideal. So why is this happening? It's basically, I mean, there's just not that much stuff in Suffolk County, so we keep looking wider, and we don't understand the geography of the area. Because great circle distance is just really easy to implement. So ways to fix this: implement a hydrophobic distance. That's how one of the people on my team put it. I really like the term. It's like, oh, there's water there. Fuck that. Or go all the way to implementing like real transit distance. They could handle cases like, oh, it's really hard to get from point A to B in London. You go like here, and the road ends, and it turns. So we see this, and that lets you kind of tune distance to whatever the particular case is. Thing to realize there, though, is we have to score that for every single one of those 102 results, which means you can't query an external API like Google or something like that, because we want this to come back in sub 50 milliseconds. You can zoom out like repeatedly on the map and tell the map to like redo searches as you're moving it around. You can, and then there's also in the filters menu you can specify a few different like levels of zoom. We don't give you that much control over like the exact number of miles though. Our user feature. So that's kind of, let's see, how am I doing on time? That's sort of the quality side of things. Give you a whole bunch of examples of, how does search quality go? Where do we do well? Where does it fall over? What are some of the problems? But that's really only one piece. There's also a whole search infrastructure side, because it's not enough to make algorithms that just return you the best results. They have to do so really quickly. There's been a fair bit of research coming out of Google was the first one that showed that as your page load time gets a bit longer and a little bit longer, users just start bailing. Doesn't take long. People do not have attention spans anymore. All of you know this. I'm happy that you're still watching me at this point in the talk. So we have sort of one of the roles of a search engineer, and a particular concentration of some members of the team is search infrastructure, which is making sure these machines stay up 24/7, 365, and are going to return results as quickly as possible on as little hardware and as little memory as possible. One side of that is on-call duty, which is not for everyone. It has some fun stories associated with it. I fixed the website naked in bed at 4 in the morning repeatedly. I've also come off a mountain from hiking to find my phone exploding and being like, oh my God, fix everything, and had my friends driving me to better internet as I was in the backseat trying to fix the website. But other than those stories, I'm not really going to talk about alerts and stuff like that. I want to talk a little bit about keeping indices in memory and kind of what it takes to do that. So I mentioned way back the inverted index. You can do a lot of stuff to compress it. And part of the reason for that is that you want it all to fit in the main memory of your machine if possible. It's for lower query volumes, it's okay if your posting lists are on disk, because you can seek to them and just read down the posting list. But at the query volume we're at, we found that we need everything in main memory. So you have to get the index, which is on disk, into Lucy's memory. That's what that's showing. And the reason why it can't be on disk, numbers over here with credit to Jeff Dean, that a disk seek is basically 5 orders of magnitude slower than main memory reference. And we just can't. We can't have that happening if we want to return these results in milliseconds. So our indices have to be in memory. That's just where we end up. So how do we get them in memory? Especially when they're originally designed to kind of let posting lists sit on disk and things like that. Well, the first thing you can do is you can cat them. Turns out if you cat your indices, that will read through everything, push them into the disk cache. I'm assuming we're using Linux for this. Push them into disk cache, and then when you're reading from the indices, you still have to do a syscall, but you're going to be retrieving things from disk cache, and it'll be fast enough. Yes, it is ghetto, but it works really, really well for something that takes 0 seconds to implement. And we don't do that anymore, but I know on good authority that a fair number of folks do. So problems with cat and just relying on disk cache like this. Well, what happens when something goes wrong and you want to less a large log on your search machine? Well, it starts taking up disk cache, and suddenly your index is out of disk cache, and things start timing out, and things start crashing, and everything comes flaming around your head, which we don't like. So kind of the next step up is something we're using now, which is VM Touch, which is a nice utility. What it'll do is it'll mmap a file and pin it into memory, so it won't be swapped out, it won't be pushed out of main memory, and then it'll just sit there as a daemon, and all that does is holds it there. So you make sure you're never doing disk references. It's still kind of ghetto. It makes it hard to track memory usage. You still have to go through a syscall to read. So I mentioned we build on Lucene. Lucene has a few different in-memory index formats, but they're not really designed for our size or scale. The instantiated index is one of them, but it has a huge amount of overhead to actually read in the index, and we already have trouble fitting indices into main memory without doubling or tripling their size. And it also isn't very fast for indices for over a gig, so that's kind of out. It's great for unit testing though. So sort of the next step is a custom solution where we build our own index format and do lots of fun stuff with mmap and direct calls.
Would it be advantageous? Could you just not? I guess the question there is how long it takes to generate the data.
Way too long for that.
All right, and then you just use like a
We've looked at again, if you do something like use tempfs and just have your index live on tempfs. I've sort of skipped over the whole index building and index distribution pipeline just because basically time constraints. But we differentially build our index on a master that's write only and push it, all our slaves pull it. So we could do something like that with tempfs and be okay to just lose the index. But in essence, it's the same as doing VM touch because you still have to go through a syscall. Like you're in memory, but you still have to do that. One might be a little bit better than the other, but we want to take the full step of going to a custom solution, which is something we haven't done yet. So if you're interested in things like that, talk to us after the talk. So this is great and fine, but what happens when your index gets to the point where you can't fit it on disk anymore? Or that would be bad. When you can't fit it in main when you can't fit it in main memory anymore, because certainly memory costs are nonlinear. They start blowing up really, really fast. And you run plenty of boxes with 96 gigs of main memory, but that's not necessarily going to be enough. So what you can do is you shard. You take your index and you cut it up into smaller pieces, and then you query those pieces independently. I'm going to talk a little bit about a few ways to do that. So we're a local search engine, so we can geographically shard. This is a fairly easy solution to put together, especially if you get to this point for the first time and boxes are falling over and you can't index during the day. You just need to fix it immediately. We did this about 3 years ago. So back then, we started in San Francisco, so there's definitely a West Coast bias to our content distribution. So what we did was we said, all right, let's find a line that splits our content about 50-50, and just draw that line through the U.S. and try not to bisect a major city. And everything west of that line will go in our west index. Everything east of that line will go in the east index, and we do some fiddly stuff around the line. And then whenever you make a search in like San Francisco, it just is dispatched to the west index. New York, it goes to east. And that works pretty well for a while. And you could probably push that for a long time, like make really weird cuts through in different places and start getting polyhedral regions. But you're going to end up with hotspots. Like San Francisco, we have a lot of content, we have a lot of traffic. It's where we started. And we're never going to be able to cut that up. But basically, we can't really cut smaller than our maximum search area. So we need something beyond that. And so for this, we use a random sharding solution, where the idea is you're going to say you have 3 shards, and what you're going to do is you're going to distribute your businesses uniformly at random across those 3 shards, and then you can when you do a search, you'll query each of those 3 shards, get back the top 10 results or whatever from each of those shards, and then do a linear time merge of those results and return the top 10 to the user. Because you've split things uniformly at random, your corpus-wide statistics like DF aren't going to be messed up too much. There's a few problems on the edges, but it works in practice. And now you can sort of split up your index arbitrarily if you want to. And now what's this diagram here is sort of explaining how we make this happen. It's with something called consistent hashing. So you take a bunch of biz IDs, which are identifiers for businesses, throw them through a hash function and map them to one of, say, 1,024 virtual shards. This number isn't particularly important. It just has to be bigger than the number of microshards you'll ever want. And then we maintain a handmade map saying, like, shard 1023 goes to number 2, et cetera, et cetera, et cetera. Now what happens when we're like, okay, these 3 microshards are too big. We need to add another shard and split things up. Well, we create a new microshard, and we pick a third of the virtual shards that point to each microshard and repoint them to the new one. So now a quarter of businesses will be going to each of the microshards consistently, and allows us to sort of reshard whenever we need. All right. How are we doing on time? Not so hot. I will go through this one pretty quickly. I'm changing gears. I didn't have a better transition than this. Sorry. I wanted to mention a little bit about our data and large-scale data processing, which is another thing the search team does. It's the search and data mining team. So we have a whole bunch of data, and now we're sharing it with you. A couple weeks ago, we released an academic data set. You need academic credentials to get access to it. That's not a problem for anyone here. And basically what it is, it's the 250 closest businesses to about 30 tech schools in the United States and all the reviews associated with them, which is about 7,000 businesses and 150,000 reviews. Business objects, it's a big JSON file with one blob per line. Business objects contain things like the city and state they're in, where they are, the number of stars, their review count, their name. Review objects are associated with business and then also contain all the review text, star rating, and then these votes for how useful, funny, or cool they are. And you also have users, so you know who wrote these reviews, what their UFCs were, the number of reviews they've written. The name is just first name, last initial, like it is on the site. So we're going to do a really quick example of what's something fun we can do with this, playing around with Mapreduce. So we're going to use the funny ratings to figure out what the funniest word in the academic data set is. We're going to use Mapreduce for this. How many of you guys don't know what Mapreduce is? Don't know. Okay. Really quick, it's a slightly restricted programming paradigm which allows you to do massive computation, like massive batch processing, that you'll be able to just throw more machines at arbitrarily to get more parallelism. And the idea is you have a mapper that will, you pass in records and it'll spit out key value pairs, and then you aggregate on those keys, and you'll get a group of values at your reducer. And we'll see an example. I don't have the time to go and do a really full, fleshed out explanation of Mapreduce. Mr. Job is Yelp's open source Python framework for writing these jobs. It's really freaking nice because Python is super friendly, and it also allows you to pipe jobs into each other, so the output of one Mapreduce step can push into another one. And coolest of all, you can run it on EMR by adding --run or EMR to your command line. Steve over here is one of the major contributors to the project and has made it even better and cooler. So you can talk to him or me about it afterwards. It really will take you like 5 minutes to download this from GitHub, get set up on Amazon. I think your first $100 of computing time is free, and then you literally have access to the same computing resources that I do, because we run our jobs on EMR. So what does a Mr. Job look like for the how fucked batch? So basically you say, this job uses Mr. Job. It's going to read JSON data, so it'll just decode it transparently for you. And then our mapper is going to be the thing that looks at every input record and says, if only look at things that are review type, and then give them a +1 vote if they have any funny votes, and a -1 if they don't. And then this stuff here is some like case and that pull off again. Damn it. It's some case and space normalization, so we just count every word in the review once. And in the reducer, all it does is it gets all the values associated with a word. So like banana, 1, 1, 1, -1, -1, 1. And it gets you the sum of the values in the word. So any ideas for what the funniest word is? Actually, shit. So, and I'm not going to show you the rest of the funniest ones because it kind of reads like a list of the top 20 swear words in the English language. So I would like to point out how easy it is to run this. So that it was that short Python batch, and then all we do is say, run in Python my script, and here's the data set, and we can pipe it into sort and tail. If you want to run it on EMR, you literally just add --run or EMR. EMR is Elastic Mapreduce. It's Amazon's sort of cloud system for running Mapreduce jobs. So you just say, here's the job to run, here's how many machines and what size of machines to run on, and it takes off for you. So you can actually have access to hundreds of machines. Though our academic data set is not big enough that you want to waste your money on 100 machines to run it. So what can we do to make this slightly less obscene? Let's try and redefine our funny metric so that instead of just saying how many, like it's the number of times you're funny minus the times you're unfunny, we'll say, let's ignore anything that the funny count is not at least 5 times the unfunny count. And this is the sort of thing data mining people do is, oh, those results suck. Let's redefine things until they work. If you do much math, you should also recognize this sort of thing. So what comes out of this? Any guesses for the new funniest word? It's not a swear word. We changed that. It is not banana. I admired your persistence, though. No, it's strippers. and here's the top 20. So we have orgasms. Oh, I didn't realize meth was in there. That's good. And apparently Lindsay Lohan is hilarious. But I really do encourage you to try this part in particular. All of this is like, I'm giving you information that you can then use. You can actually go build a small search engine. You can also go download EMR or download Mr. Job. You can't download EMR. You can download Mr. Job, get on EMR, and actually check for yourself that this is right. But that's about my talk. Any questions? What's up?
I missed the first part of your talk, so ignore me if you're... how do you prioritize the branching and the fast way? So it has to go through all those edge cases.
So basically, it seems like we end up with a fairly complicated model. How do we keep it quick? Profiling? So it's,
or how do you decide what's more important?
It's actually a very good question. I don't know that I have any philosophy that I've thought out to the point of being able to write it down. But we do a fair bit of, before a major change is going to go out, I wrote a tool called the Diffinator, which we can run through old search logs and compare what's going to change and kind of predict the effect on metrics. In addition to doing this A/B testing, we can take a look at that and just how widespread of a problem this is versus is it actually going to have an effect on performance. Usually the answer is whatever changes you make, you can't make performance worse. It would be nice if you could make it better, but you certainly can't make it worse.
So it sounds like it's all done by hand.
Oh yeah.
Okay.
Yeah, we're not I'm not going to pretend that we're the most advanced search team in the world. We're not Google, but it's also pretty exciting because there's a hell of a lot of large problems left to solve and cool tools we're building, and it's a less explored domain. So, yeah. Other questions, maybe?
I know early on, but I did notice that a lot of things you do are similar to what you're trying to find these unintuitive connections or whatever.
That's interesting.
It seems really useful to exactly what you meant to do.
I haven't actually done as much research into Watson as perhaps I should have. There's sort of a trade-off between reading papers and actually building things and keeping up with stuff, especially for me who I didn't go to grad school and I didn't learn to like just read papers in like 2 minutes. I guess I sort of think of that as the sort of my answer is the same as when people ask me why we don't buy one of Google's like search boxes, like they're boxes that you plug in and now you have search over this thing. It's like that's essentially what we had when we like pulled Lucene, like we started up Lucene and we just like built it, or like we used Solar, which is a little more out of the box thing built on Lucene. It doesn't have sort of domain specific optimizations, which is most of what I talked to you about, and most of the reason like we're better at this than I think City Search is, or some of the other folks. So I think buying a Watson, you would end up hiring a Watson team that sort of optimizes that and basically does what the search team does now. It's my opinion on it, but probably time for one question. Oh, yeah, one question. The Lucene defines its own index format, I think. So I forgot to mention this. Introduction to Information Retrieval by Manning, Raghavan, and Schutze is free online. If you search for this name, it'll come up number 1. It's a really good introduction to IR, and I think like chapter 4 or 5 explains at least the basic concept of how this index works. It's not MySQL backed. I think I'm already over time. I'm going to be around if you want to ask me questions, though. So, sorry.